All right, so our new topic has kind of a weird name. It's called stoichiometry. That's this word here. It actually comes from two Greek words, stoichion meaning element and metron meaning measure. So it's all about measuring out the amount of elements you have in a chemical reaction. So the nice thing about this is once we know how to apply this technique, we will be able to do quite a few labs where we use this concept to make predictions about chemical equations. So it really does put together some of the big ideas we've been working on all year. So there's some steps here that we'll work through. We're going to do one problem fully together. I'll help you get started on a second problem. And then that'll be it for today. This is kind of a very involved sort of problem. It's not one that you can just sit down and do in 2 minutes. So looking at our first reaction, we have both the chemical equation and the written description. So it says lead, that's Pb, will react with hydrochloric acid, which has the formula HCl, to produce lead 2 chloride, that's PbCl2, and hydrogen gas. And the first step on doing any of these problems is balancing the chemical equation. So let's take care of that step together. And I'm going to go ahead and use diagrams like we've done before. So for lead, that's just metallic lead. I'll just put Pb in a circle. That's my lead atom. The HCl, it says it's hydrochloric acid. So we've touched on this. We haven't really done a full unit on acids yet. We will. But with acids, you always have an aqueous solution, and you have a hydrogen, an H+ ion, and a negative ion. So instead of drawing this together like a molecule, I'm going to separate it out into an H+ ion and a Cl- ion. So this actually would be aqueous. We could put AQ here, but that's fine. And those will react to make PbCl2. So here it did say that it's lead 2 chloride. So that means in this compound, it's got a +2 charge. So I'm going to write Pb2+. And it's going to link up with 2 chloride ions. So chloride ions are always Cl-, same as they were here. And there are 2 of them in the formula unit. So I'm going to draw 2 of them here. So that's how I'm going to represent 1 unit of PbCl2. H2 is a molecule, 2 hydrogen atoms stuck together with a covalent bond. So I'll represent that like that. So doing a quick check of balancing, I've got 1 lead, 1 lead. It picks up a charge here, but that doesn't change the fact that it's a lead atom. It just lost 2 electrons. I've got 1 hydrogen, 2 hydrogen in the hydrogen molecule. So I do need to double HCl, the coefficient of 2. Again, I can't change the subscripts. I can only multiply the entire quantity. And so that means I have a second pair of H+ and Cl- ions. So now I've got 2 hydrogen, 2 hydrogen. I've got 2 chlorine, or 2 chloride ions in this case, same here. So it is balanced with just a coefficient of 2 in front of HCl. Even though I don't have to write it, for the purposes of this activity, I'm going to go ahead and put a coefficient of 1 in front of the other substances, because the mole ratios are going to be very important in finding out how to answer the question. So that's step 1. We balance the equation. And next we want to identify what's given with units and what we want to find. So it says how many moles of HCl are needed. That's one of our questions that we want to answer to completely react with 4 moles of lead. That is our given in this case. And I'm going to go ahead and put that into my chart. So I call these BCA charts, for before, change, and after. We're going to look at what's present before the reaction happens, what change occurs, and then what's left after the reaction. So I can go ahead and fill in that I have 4 moles of lead before the reaction happens. I'm just putting it below lead in the table. I want to actually think about how many moles of HCl I would need. I'll get to that in a moment. And one thing you can always assume is before the reaction occurs, you don't have any of the products. So the reaction hasn't happened. So I haven't made any moles of product yet. So those would both be 0 moles. Now, if I want to react lead with HCl, the 1 to 2 coefficient is quantity, right? I need always twice as much HCl as lead. If I have 4 moles of lead given in the problem, then I'm going to need 8 moles of HCl to react completely, because the mole ratio reflects the particle quantities, right? And so I can represent the change that occurs with minus signs here. So I'm going to convert or lose 4 moles of lead, unreacted lead. And for now, we're always going to assume that they both get reacted completely if they're in the correct ratio. So I'm going to lose 8 moles of HCl as the process of the reaction occurs. And then I'm going to add product with the same ratio. So it's a 1 to 2 to 1 to 1 ratio. That means this 1, the 1 to 1 ratio should be with the amount of lead that reacts. Well, if 4 moles of lead reacts and it's a 1 to 1 ratio, that means I'm going to create 4 moles of PbCl2 and also 4 moles of H2. Oops. So when it's all said and done, I have 0 moles of unreacted lead. I have 0 moles of unreacted HCl. I've created 4 moles of PbCl2, and I've created 4 moles of H2. Okay. And that actually answers B. B says how many moles of lead 2 chloride? 4. And how many moles of hydrogen gas? 4 would be produced. So this is actually 4.0 moles each. For B, and the answer to A was how many moles of HCl are needed? That's 8 moles. Okay. So that answers the question, but I am going to teach you a way to analyze this one step further. And what we're going to look at in this kind of confirmation check is conservation of mass. Okay, so one of the key ideas in chemistry is that when you undergo a chemical change, you have a certain mass of atoms that you started with. You shuffle them up into different compounds, but you didn't create atoms and you didn't destroy atoms. So the starting mass, if I were to figure out the mass of everything I started with, it should equal the mass of everything that I end with. All right. And so we're going to do that check. And this is a really good review of mole calculations. So what I want to do is figure out if I have 4 moles of lead. So I'm going to jot that down here. 4 moles of lead. I want to know what its mass would be in grams. Okay. So to do that, I've got to go to the periodic table. Let me bring them up here on the screen. So I need to look up lead on the periodic table. Lead is over here, and its molar mass is 207.2. That means grams in 1 mole. So I'm going to go back. I'm going to actually jot that number down here. So it's 207.2 grams per mole for lead. That one's easy because it's just a pure element. To do the molar mass for HCl, I need to add up the molar mass of hydrogen and chlorine. So hydrogen 1.01 grams per mole plus chlorine 35.45. That's going to be 36.46 grams per mole. Jot that down here. For PbCl2, I'm going to have to add up 1 lead plus 2 chlorine. If I do that, I'll go ahead and give you that number. That actually comes out to be 278.1 grams per mole. And again, that's just taking lead and adding in 2 molar masses of chlorine. And then H2, remember H2 is 1.01 as a pure atom, but we have 2 of them in the formula. So it's going to be 2.02 grams per mole. And that's one thing that when you do these problems, either it'll be given or that'll be a first step to figure out the molar mass of each substance involved in the reaction. So I'm going to take 4 moles of lead and use the molar mass as a conversion factor. So I want to multiply in such a way that moles will cancel. And that's exactly how the molar mass is set up, right? It's 207.2 grams in 1 mole. And that should make sense. If that's the grams in 1 mole, I want to multiply by 4 to figure out the gram amount in 4 moles. So we'll go to the calculator. 4 times 207.2 equals 828.8. And one thing I like to do on this chart is be consistent in the number of decimal places I report. So I'm going to be a little bit imperfect maybe on the sig fig rules, but I do want to just record all of these. I'll round them to the nearest tenth, and that we're going to be adding these up. So it makes sense, or it's kind of nice to have the same number of decimal places when you add them up. So 828, oops, back to my So 828.8 grams of lead is the mass of 4 moles. I'm going to jot that down right underneath the 4 moles because it's equal. That 4 moles equals 828.8 grams. So that's the mass of one of my reactants. I'm reacting it with 8 moles of HCl. I'm going to do the same calculation for HCl. So I'm saying that it will react with 8 moles of HCl. I'm multiplying it by the molar mass, the grams per 1 mole, which I gave you in that previous step, 36.46 grams. Grams of HCl in 1 mole of HCl. That's the meaning of molar mass. And just like here, I could have shown cancellation of units. I'm canceling moles. And so it just take 8 moles times the mass of 1 mole, right? So I'll go 8 times 36.46 equals. And again, I'm going to go ahead and round it to 1 decimal place. So I'm going to call it 291.7 grams. That would be the amount of HCl, hydrochloric acid, that reacts. And again, I'm going to write it right below because it's the equivalent amount in grams. These are easy. I have 0 moles. That's 0 grams. Don't need to do any calculating there. So again, we're talking about conservation of mass. What I really want to know is, what is the total mass before? I want to add up these two individual masses, and I'm going to jot it down here as a total. So 828.8 grams of lead reacting with 291.7. I'll go to my calculator again just to double check. So 828.8 plus 291.7 is 1,120.5. And remember, when you add, paying attention here, we want to keep the decimal place when we add. So when you add them up, thinking about significant figures, you don't lose any decimal places. So I'm going to jot that here. 1,120.5 grams. And what that is the total mass that's reacting. It's the total mass of reactant before anything happens. So we could do the same thing on the change line, like figure out how many grams reacted, but here it's just everything. So you'd be losing all 828 grams. You'd be losing all 291.7 grams. But we do want to know how much product we create. And if our chemistry is correct, mass should be conserved. So I want to do this same calculation for my predicted product amounts. So I want to do the conversion for 4 moles of PbCl2 and 4 moles of H2. So same idea. I'm really just multiplying by the molar mass, the grams in 1 mole. So if I want to show cancellation of units, I can do that. Go back and look at the molar masses that I added up. 278.1 grams per mole for PbCl2. That is the mass in 1 mole. And again, this is the mass in 1 mole. If we have 4 moles, it should make sense that we're multiplying by 4. So I'll take 4 times 278.1 equals, and again, I'll be consistent to the tenths place, so 1,112.4. And that would be, again, the mass of PbCl2 that forms in the reaction. So that's equivalent here. So just kind of doing a quick check, that mass is very close to the starting mass, the total starting mass. So if my chemistry is correct, that's saying most of the mass ends up in PbCl2. That should kind of make sense because the lead is a very heavy atom. It's got a large molar mass. Cl is a fairly decently large molar mass. So PbCl2, 4 moles of it should have a pretty large mass, which it does. And so our last calculation then is for the H2. We're predicting 4 moles is produced, and we're using the molar mass of 2.02 grams per mole. So again, if we multiply by grams per 1 mole, moles will cancel. That will come out to be, I think we can do that in our head maybe, 8.08 grams of H2. And if I keep it consistent to 1 decimal place, I'm going to round that to 8.1. Because if I were to add these anyways and round for sig figs, I would need to round to the 10th place. So that is my total mass produced, what's left after the reaction happens. And if you check it out, so that would be 1,112 plus 8, which is 1,120. And then I'll take care of my decimal. 0.4 plus 0.1 is 0.5. So kind of magically, it all works out correctly. The mass that I started with total equals the mass that I ended with. And that, although this is a very complex, many-step problem, at least we know that if we've done it correctly, there's a way to check it out. If you do one of these problems and you see that the mass is different, there's something wrong. And that's the challenge in this sort of problem. It has so many steps that it would need to pinpoint where things went wrong. It could be in adding up the molar mass. It could be your mole ratio. Of course, if you balance the equation wrong, that's going to throw everything off. But you have really, really high confidence that things are correct if you do the check and they come out the same. All right, that's a lot for the first day back from break. Any questions on steps that we just did? Yes.
So in the beginning, how did you get 4.0 moles?
It was given in the problem.
Okay, and then the second one, since 1 to 2 ratio, is double it.
Exactly. Yep. So you would have to be given at least one either starting amount or ending amount and work from there. Yep. Other questions? All right. So let's move to number 2. I'm going to help you guys get started on it. And then I'll have you guys finish the last few steps and see if mass is conserved. If mass is conserved in your calculations, chances are you did things correctly. Okay, so the written description of the reaction is calcium hydride, that's CaH2, reacts with water, H2O, to form calcium hydroxide. Hydroxide is a polyatomic ion with a -1 charge, so the formula is Ca parentheses OH2. And then hydrogen gas, again, is a product in this reaction. So calcium hydride is an ionic compound. So hydrogen is a nonmetal, calcium is a metal. So if I'm representing that compound, if I go to my periodic table, calcium is a group 2 metal. Those all have a +2 charge when they're ionized. So I'm going to write it as Ca2+. It is joining up with hydrogen, and specifically it's the hydride ion version of hydrogen. So hydrogen, in the previous problem, we said it was a H+ ion. That's the way it behaves in an acid. Here, hydrogen is actually gaining an electron, which nonmetals typically do. Go back to my periodic table, make it a little smaller. So hydrogen only has 1 electron. It can lose that electron to be an H+, but if it gains an electron, it has the configuration of helium, so it's stable. It's a -1 ion. So I'm going to represent that as H-. There are 2 of them in the compound, so I'll draw 2 of them in my diagram, something like that. H2O, we've seen H2O's molecule a lot, right? It's a bent molecule, 2 hydrogen, 1 oxygen. Calcium hydroxide, another ionic compound. Calcium is still a +2 ion. And then we have a question of how we want to represent hydroxide. So again, a little review. Polyatomic ions are like molecules that carry a charge. There are 2 of them. So I'm going to make a little OH on the side here. And all together as a unit, the hydroxide ion is -1. and I have 2 of those. So I'm going to draw another grouping of OH minus over on the right-hand side. So the calcium is a +2. Each hydroxide is a -1. We have charge balance in the formula unit, which we always want to have with ionic compounds. And then H2, it's just a molecule of 2 hydrogen stuck together with a covalent bond, like that. So just doing a visual check of our quantities, I have 1 calcium, that's good. I have 1, 2, 3, 4 hydrogen atoms. 1, 2, 3, 4 hydrogen atoms. So far, so good. 1 oxygen, 2 oxygen, right? That's a problem. So I can't change the formula, right? I can't just make it H2O2 because that's a completely different substance. That's hydrogen peroxide. It's not water. But I can double the quantity by adding a coefficient of 2, which means I'm going to draw in a second water molecule. The whole thing is doubled. Now I have my 2 oxygen that I want, which matches up 1, 2. But I've added more hydrogen. Now I have 1, 2, 3, 4, 5, 6 hydrogen, and I only have 4 over here. Okay, so I've got to do something to one of these, put a coefficient. I don't want to mess with calcium hydroxide because if I double it, it's also going to double the calcium and the oxygen and the hydrogen. So the way we want to balance this is with a coefficient of 2 here, which gives you a second hydrogen molecule. And now we've solved our problem of having 6 hydrogen, 1, 2, 3, 4, 5, 6 on that side. Calcium checks out, 1 and 1, hydrogen 6 and 6, oxygen 2 and 2. I'll go ahead and put in my coefficients of 1, even though I don't really have to, just so we're absolutely sure what we have. Okay, so that's the first step, right? Balance the equation. Next, we want to look at what we're given and what we want. It says how many moles of hydrogen gas and calcium hydroxide will be produced if we start with 5 moles of water reacting. That's our given. I'm going to go ahead and plug that into the equation. And maybe I'll highlight it just so we know that was a given. We didn't do any calculating for that. That's what we start with. Okay, so if we know that, how many moles of hydrogen gas and calcium hydroxide will be produced, and how many moles of calcium hydride react. So let's start here. We'll work our way to the left. We do know that before the reaction happens, we don't have any product. So I'll put 0 moles on the before line. Again, it's before, change, after. The amount of calcium hydroxide that needs to react with H2O is in a 1:2 ratio. I need more hydrogen, and I specifically need twice as much water, not hydrogen, H2O. If I'm going to react 5 moles, the proper amount of calcium hydroxide, or calcium hydride, needs to be 2.5 moles. Because it has to occur in a 1:2 ratio to react equivalently, so that each of them is used up and completely converted to product. Okay. So I'm using the 1:2 there to figure out the smaller amount here. The 1 needs to be 2.5, and the twice as much amount is 5.0. In the reaction, both of those are going to be converted completely. We'll assume that's true at first. That won't always be true going forward. And then the coefficients are reflected in the change line. So if I use up this much calcium hydride and this much water, the coefficient here is 1, and the coefficient of here was 1. So those two should be equivalent in their mole amount. I'm going to make 2.5 moles of calcium hydroxide. This one has a coefficient of 2, so look at it a couple of different ways. This needs to be in a 1-to-2 ratio in how much is produced, so it needs to be twice as many moles. Or, checking back to our reactant side of the equation, these have the same coefficient, so the same mole amount should be involved in the change line. So the change line is what reflects your coefficients, because the chemical equation is telling you what happens when the reaction occurs. So just continuing, we're going to assume that we use up all of the calcium hydride, all of the water. We're going to produce 2.5 moles of calcium hydroxide. And we're going to produce 5 moles of H2. Okay. So in answering the questions, how many moles of hydrogen gas would be produced? 5 moles. And how much calcium hydroxide is produced? That's the CaOH2, 2.5 moles. And then how many moles of calcium hydride react? That is the half amount, right? 2.5 moles. So on the most basic level, we've answered the question. What are the quantities involved here, right? Questions up to that point. Okay, so to finish it out, we want to check for conservation of mass. I am going to go ahead and give you the molar masses so that you don't necessarily have to add those up on the periodic table. That'll save you guys a step. Let me give you those values. So CaH2 would take calcium and add in 2 hydrogen. Calcium 40.08, hydrogen 1.01, but times 2 because there are 2 of them in the formula. And that is 42.10 grams in a mole, grams per mole, grams per 1 mole if you want to think about it like that. H2O, if we add them up, H is 1.01 grams per mole times 2. Oxygen is 16.00 grams per mole. So adding those up, that is 18.02 grams per mole. When we do calcium hydroxide, we're going to add up 1 calcium, 2 oxygen, right? Because this is multiplying the entire OH unit, and 2 hydrogen. If you add those up correctly, it is 74.10 grams per mole. And then H2 again, that's just 1.01 times 2 because the molecule has 2 hydrogen in it. 2.02 grams per mole. Okay. So we have our conversion factor. Again, what we'd like to know is what mass do we start with here? Total, is that the same mass that we end with? If it checks out, then we know our chemistry is correct. So I'm going to get you started, and then I'll let you guys check the calculations on your own. So I have 2.5 moles. Yep.
Why is the last hydrogen not 4.04?
Good question. So you're looking at the fact that you have 2, right?
Oh, yeah.
Yeah, so the question was, why don't we list the molar mass as 4.04? Because what I want to know is the grams per mole in H2 always, right? So you could have 3 H2 in a problem. You could have 5 H2. You could have 1 H2. But if I'm just doing a conversion for hydrogen, separate from the idea that in this particular equation there's twice as much. That molecule itself will always have 2.02 grams in a mole of H2. Yeah, that is a tricky part. We've already accounted for the 2 by saying that 5 moles is produced, right? Because it was double the coefficient of 1. Yeah. Okay, 2.5 moles of CaH2. I want to convert that to grams. So it's just a straight multiplication of the molar mass, which again, you'd have to go to the periodic table and add this up. That's the grams in 1 mole. So again, that's the grams in 1 mole. You've got 2.5 moles. That's why we're multiplying here. We'll go to the calculator. 2.5 times 42.10. It's 105.25. And again, my rule of thumb is just go to the tenths place and then add up to the tenths place. So I'm going to report that as 105.3 grams of CaH2. So again, just rounding that here. And again, that is equivalent to 2.5 moles of CaH2. So I can do a little equal sign. (105.3 grams). Okay. I want to do the same calculation for each other substance. So I want to convert 5 moles of H2O to grams of H2O. Using the grams per mole conversion. Adding those up should give me the total mass before anything happens. And then we want to do the same thing for what we're predicting happens after the reaction. We want to take 2.5 moles of CaOH2 times its molar mass, grams per 1 mole. And then 5 moles of H2 is produced. You want to multiply by its grams per 1 mole. And when you add those 2 up, your totals should be the same. If it's not, there's something wrong in a calculation. Okay, I will tell you the magic number that you're looking for here is 195.4 grams. If you get that before and after, you've done things correctly. All right. So I'm going to let you guys take it from there. I'll kind of walk around the room and answer questions. But if you can get to that value, you are on the right track with this type of problem. Okay?
After that, are we done?